Welcome all. I am Urchan BS. I am going to teach you the digital techniques subject which is having a code of 22320. This subject consists of theory paper and practical examination. For theory there are 100 marks which consist of a board theory exam for 70 marks and progressive assessment of test 1, test 2 and micro projects for 30 marks. For practical there is a external practical exam of 25 marks and a progressive assessment of your manuals for 25 marks. In all, total weightage for this subject is of 150 marks. We will start with the first unit of this subject, that is number system and codes. At the end of this unit, you all will be able to convert the given number into the specified number system. You all will be able to perform the binary arithmetic operations. You all will be able to perform the BCD arithmetic operations, and you all will be able to convert the given coded number into the other specified code. First we will see some definitions. What is a signal? A signal gives certain information of physical quantities such as temperature, pressure, distance, etc. There are two types of signals. One is analog, second is digital. Analog signals are continuous in nature. That is, we get information of analog signals at any instant of time. For example, we will sine wave. The sine wave gives the information at any instant of time of a particular signal. The digital signals are discontinuous or discrete in nature. That is, they give information for particular interval of time only. The example for this is a computer generated data. Next we will see what is a logic. It is a statement which is true for some condition and false for other condition. The example given over here is a bulb which remains on if switch is on. A bulb remains off if switch is off. Switch on can be considered as a true condition. Switch off can be considered as a false condition. The statement which has two distinct outcomes is called as a binary logic, which considers two logic values, that is logic 1 for high level, logic 0 for low level. There are two types of logics, that is positive logic and negative logic. The low level is represented by a 0 volt in case of positive logic, and high level is represented by a 5 volts. In negative logic, low level is represented by 5 volts and high level is represented by a 0 volt. Now we will see what is a radix or a base. The number of values that a digit can assume is nothing but a radix or a base of that particular number system. For example, if we take a decimal number system which is having a base of 10, hence every digit in the decimal number system can assume any one of the 10 values. The number system's range starts from 0 and ends with the 1 less than the base. That is, in case of decimal number system, the number starts from 0 and ends with the 9, that is 1 less than the base, that is 10. There are various number systems: the binary number system, octal number system, decimal number system, hexadecimal number system. The binary number system is having base of 2. The range starts from 0 to 1. Octal number system is having base of 8. The range starts from 0 to 7. Decimal number system is having base of 10. The range starts from 0 to 9. Hexadecimal number systems is having base of 16. The range starts from 0 to 15, from which 10 to 15 is represented as A to F, that is 10 as A, 11 as B, 12 as C, 13 as D, 14 as E, and 15 as F. You can see the examples of various number system in the given table. Next we will see different binary number formats. We can write the binary numbers as a sequence of bits as shown in the following table. There are different formats shown in the table, that is bit, nibble, byte, word and double word. A bit is having a size of 1 bit, a nibble is having size of 4 bits, a byte is having size of 8 bits, or in other words, two nibbles together forms a byte. Next, a word is having a size of 16 bits, or in other words we can say 2 bytes together forms a word. Next is the double word, which is having a size of 32 bits. In other words we can say two words together forms a double word. We can convert any number system into the another number system, that is we are going to study the conversion of number systems. We will see conversion from decimal to base R system, that is decimal to binary, decimal to octal, decimal to hexadecimal conversion. After that we will see conversion from base R, that is from binary to decimal, octal to decimal, hexadecimal to decimal conversion. After that we will see conversion from base X to base Y. For example, we can convert any base into the another base, that is base 2 can be converted into the base 8. We will see one by one. First we will see conversion from decimal to base R system, that is how the decimal number can be converted into binary number system, octal number system and hexadecimal number system. There are two cases over here. One is the integer part of the decimal number system, second one is the fractional part of the decimal number system. In case of integer part of the decimal number systems, we are going to divide the integer part by a required base successively till the quotient becomes 0, or in other words we can say we will divide the decimal number system till the divisor till the dividend becomes less than the divisor. After the complete division, we are going to arrange the remainders of successive divisions in a reverse order to get required equivalent number of base. In case of fractional part, we are going to multiply the fractional number by a required base successively till we get the result as a 0. After the successive multiplication, we are going to accumulate integer part of all multiplications in a normal sequence to get the fractional part of the equivalent number of required base. Now we will see how the decimal to binary conversion can be done. That is how base 10 to base 2 conversion is to be done. Here we have taken three examples. First one is the decimal number 31, which we have to convert into the binary number. For that, we have to divide it by a 2, as the binary number is having a base of 2. During the division, write down the remainders successively. Divide the given decimal number until the dividend becomes less than the divisor. Now, in this case, first, when 31 is divided by a 2, 2 15s are 30, the remainder will be 1, which will form a LSB of our required binary number. Perform the successive division till the dividend becomes less than the divisor. In this example, at the end, the dividend becomes 1, which is less than the divisor. Now stop the division and write down the dividend as a remainder, which is the MSB bit of our required number. After the division, write down the remainder, that is our required number, our required binary number from MSB to LSB. Second example is 19. Perform the successive division. After the first division, the remainder which we get, that will be the LSB part of our required binary number. At the end of this division, we will get again one remainder which will form the MSB part of our division. Arrange the numbers from MSB to LSB. We will get 10011 as a binary number for decimal number 19. Third example is 0.625. That is a fractional part. Now to get binary number, we are going to multiply successively by a 2. First, 0.625 is multiplied by a 2, which will give 1.250 as a result. Write down the integer part of this multiplication aside, that is 1. Again multiply the fractional part, that is 0.250 by a 2, which will give you result 0.500. Again write the integer part 0 aside, multiply 0.500, that is fractional part, by a 2, which will give you 1.00 as a result. Again write down the 1, that is integer part, aside. Perform the multiplication till we get the result as a 0, or repeat this for at least 4 to 5 times. After the successive multiplication, write down the integer part in a sequence from MSB to LSB, that is 101. The first integer which will we get, that will be our MSB part. The last integer number which we will get, that will be our LSB number. These are the examples which you can perform at your own. We will discuss during our online session regarding these examples. Next conversion is decimal to octal conversion. For performing decimal to octal conversion, we are going to divide the given decimal number by 8, and we are going to multiply given fractional decimal number by 8. In this there are three examples. First one is 31, which is divided by, which is a integer number, that's why it is divided by 8 to get the required octal number. In this, 7 and 3 are the remainders, from which 7 is the LSB part, 3 is the MSB part. Again we are going to arrange from MSB to LSB, that is 37, to get the required octal number. Second example is 64. To get its equivalent octal number, we have divided it by 8. After division, we will get 100 as a octal number. Third example is 0.513, which is a fractional number. To get the required octal number, we will multiply it by 8, which will give the octal number 4065. Again, these are the example of decimal to octal conversion, which we are going to discuss in our online session. Third one is the decimal to hexadecimal conversion. To get hexadecimal number, we are going to divide by a 16, or we are going to multiply by a 16. There are again I have taken three examples. First one is the 31, which is a hexadecimal number, which is a decimal number. We will divide it by 16 to get the required hexadecimal number. After division, we will get 15 and 1 as a remainder. We can write this 15 as a F, as the 10 to 15 numbers are represented by A to F in case of hexadecimal number. By arranging from MSB to LSB, we will get 1F as a hexadecimal number for the decimal number 31. In the second example, 64 is divided by 16 to get its equivalent hexadecimal number, that is 40. In third example, 0.85, that is a fractional number, which is a decimal number. To get hexadecimal number, we are going to multiply it by a 16. After first multiplication, we will get the result 13.16, from which 13 is an integer part. Write down it aside, that is 13, which can be written as a D. Perform the multiplication for 2 to 3 digits. In this, I have performed only for 2 digits. After second multiplication, I have got 9.60 as a result. 9 is the integer part. Again, take it as our hexadecimal number. Arranging from upward to downward direction, we will get 0.D9 as a hexadecimal number for the 0.85 decimal number. Again, these are the example of decimal to hexadecimal conversion, which you can perform at your own.